All right. Hello, everyone. So just a reminder before we start to silence your phones, Game Boys, or any device you may have. All right. So we're here to talk about latency on Call of Duty Black Ops 3. So Call of Duty is a fast-paced, multiplayer, first-person shooter. And in such a competitive game, you want everything to feel smooth. Because when everything feels smooth, it's just an amazing experience. It feels like everything is effortless. You can pull out amazing trick move like that. Your mind almost slips into a no-mind kind of flow state where the character on screen becomes an extension of your body and the controller in your hands disappear. It becomes almost magical. And any manifestation of latency can break that amazing experience. So we want to make sure that the game stays smooth and it stays responsive. So we try to avoid every frame of latency that we can. So to give you an idea of what one frame of latency means, because in this talk we're going to talk a lot about milliseconds, which is the unit of time that we use to measure latency. Let's look at this graph. So 2300 milliseconds is 2.3 seconds, and this is the average reaction time of a driver in a car. So let's say there's an accident in front of you and you need to react as fast as possible, hit the brake to save your life. Studies have shown that the average reaction time is about 2.3 seconds. Professional race car driver can do it in 350 milliseconds, which is about in the ballpark of pro gamers, people who train and are very focused on what they do. That's their reaction time. 300 milliseconds, that's the time it takes to blink your eyes. And in Call of Duty, an assault rifle can kill you in 150 milliseconds. So don't blink ever when you play. And 10 times faster than that is 16.7 milliseconds. That's one frame of latency in the game. So a little bit about me. So my name is Ben Goyette. I'm an engineer at Activision. I've been there for actually a short amount of time. It's my second year there. Before that, I was the lead engineer on the indie mech shooter called Hawken. And before that, I was working at Ubisoft Montreal as a lead. Shipped a few multiplayer games there and worked on network engines. And even before that, almost 15 years ago, I was working in motion capture. I was making mocap software called Motion Builder. So we were making special effects and real-time animation tools for Hollywood movies. So when I started working with Treyarch, because I work at the Central Studio at Activision, so we're a group who supports the studio owned by Activision. And when I started working with Treyarch, their problem was that it feels like we have more latency, and that came from the playtesters who were playtesting the game every day. So it was a vague problem. It was just a feeling of latency, like a feeling that something was wrong, something was a bit off, and it wasn't reproducing every day. It was just sometimes people were reporting that. So we were not sure if it was really a problem. It was hard to prove that it was a problem, so it was hard to fix. And many developers had different remedies and theories of what was the problem, but we didn't know if it was placebo or not. So the team wanted to have like a fresh set of eyes looking at the problem, like to get a new perspective to see if I could find something else that nobody had found before. So what is latency? So for us developers, we know what it is. We're very used to that concept. We know that everything we do with the hardware takes some time. So there's no magic there. Every time we do something with the hardware, whether we send a packet on the network, read from disk, write in memory, compute something on the CPU or GPU, we know that we do something, it's going to take time. And we're pretty good actually at measuring the latency in all of these systems. And we're pretty good at creating the illusion of putting all this together on screen to create the illusion that everything is responsive. So for us, it's a known concept. But for the players, it's a different concept. It's a much broader concept. It's when the gameplay experience feels imperfect. They're going to call it lag. They're going to say, oh, this game lags, right? So it can be typically a delay between a button press and a reaction on screen. It could be stuttering animation, object popping up on screen. It could be hitches, frame rate problems. But it can also be the perception of unfairness. So this is very broad. So it's like they expect something to happen in one way and it doesn't happen that way. So they feel like there's a problem there. So they're gonna say that your game lag. And so as you see, it's the point I want to make there is that it's not just about the ping. It's a much broader concept. So what this means is that for the players, it's kind of a different definition of what latency means. So we can get in this situation where all our classic tools of profiling are telling us that all our systems are okay, but in the playtest, the players are experiencing latency. So because of that, we came with the need that, okay, so we need to be able to look at the problem from the perspective of the player's eyes. We need to see the perceived latency, not just what our tools are measuring. So we came up with the idea of doing like a Mythbuster style investigation. You know the TV show Mythbuster, where they blow stuff up and then they record with high-speed camera and then they look in slow motion what's going on and they find some crazy stuff that they never thought was there. So we thought, let's do the same thing with an high-speed camera and record the actual screen that the players are seeing. So two things we wanted to measure, controller to screen and screen to screen in multiplayer. So in this talk, I'm going to talk about the current tech that we started with on Call of Duty and the classic tools that we use to fight latency. Then I'm going to show you my camera setup that I use to record. And then I'm going to show you a bunch of tests that I did to measure the screen-to-screen latency and the controller-to-screen latency. I'm going to show you what I found there and how we solved some of the problems that we found. So let's start with the current technology. So Call of Duty is a client-server game. So that means that all the clients are connected to a central dedicated server. So what this means for latency is that every packet from a client needs to go through the server to reach another client. So there's always an additional step. There's no direct peer-to-peer connection to send the data. And it also means that the server is authoritative of the gameplay state. So the server takes all the decision about the gameplay state. So there's some level of consistency there with the gameplay state, which helps with the perceived latency. The server needs to send the world state to all the clients. So it's going to send updates frequently at a fixed frequency. These updates are called snapshots. And one snapshot contains actually everything that you see on screen for one frame. Everything is there in the snapshot. So all the states of all the entities, all the position, everything is contained. So that's a huge block of data. So what we do to reduce its size, we do delta compression against the previous snapshot that was acknowledged by the client. So with this delta compression, we're able to compress them to quite a small size, and we actually are able to fit them in one UDP packet, in the MTU of one UDP packet. Why do we use UDP? Again, it's for speed. It's to reduce the latency. UDP is very fast. There's no error correction. But the problem is that some packets might be dropped, right? But turns out that we don't really care about packet loss with this system, because since there's everything in one snapshot, if one is dropped, we don't want to try to resend it or detect the drop. We know that there's another one in flight incoming, so we know that we're going to get fresh data anyway coming later. The rate of the snapshot is lower than the frame rate. So to be able to display smooth animation on the screen, what the client is going to do is going to interpolate between two snapshots. So he's going to have to buffer one snapshot and wait for the next one to arrive to be able to have two snapshots to interpolate. So this is going to introduce a little bit of latency for the sake of smoothness on the screen. In the other direction, so the client needs to send his intentions back to the server. So he's going to send them in a packet that we call the commands. The commands contains all the intention of the player, so jumping, shooting, anything the client wants to do. These packets are very small, so we can send them very fast. We also send them with UDP. But in this case, we care about reliability. We don't want to drop commands because some actions would not register. So what we do there is we just, in each command packet, we replicate all the commands from the previous packet until the server finally acknowledges that he received them. So we kind of just spam the socket with all the commands until the server finally tells us, stop spamming, I received them, kind of thing. So we can do that because we can afford the bandwidth, because they're so small, we can just duplicate them, and we do that for the sake of latency, so we don't have to do some error checking and detect that one command was dropped and resend it. Client-side prediction. So this is another concept we use on the Call of Duty engine to reduce the latency, and it's something that all the first-person shooter do on the market. So what it does is that when you press a button on your gamepad, we want the reaction on screen to appear instantly. So what we do, the client is going to predict the result of that command right away and display the result immediately on the screen. Because if we didn't do that, we would have to put the command in a command packet, and we need to reach the server. Server needs to process that, needs to put that in a snapshot. Snapshot comes back. And this whole round trip is unacceptable for a Twitch first-person shooter like Call of Duty. So the client is predicting the result locally, and yeah, it gets instant responsiveness there. And the next snapshot that's going to come in using that command is going to confirm that the prediction was right, so the client can just move on. Sometimes there's going to be a missed prediction there. You're going to feel it when you play. If you get some rubber banding, that's because you predicted you were going to be able to move in one direction, and then the server told you, you're a bit there instead, so you're going to kind of rubber band. So you can feel the correction there. But with this concept comes an artifact. So with this artifact, to illustrate it, this is a sequence diagram, a UML sequence diagram. For those who don't know, it's just a way to modelize interaction between two systems. So in this case, the server talking to the client. And the twist that I do with my sequence diagram is I use diagonal line to represent the latency of how much time it takes. So in this case, you see the server sends a snapshot to the client, and it takes, let's say, 50 milliseconds to reach. So what this means is that the server is in the present, right? He has the official state. So by the time it takes for the snapshot to reach the client, what the client is rendering on the screen there, it's in the past. It's a past state. But we let the client move his camera locally with client-side prediction, so he's going to be able to move a little bit. So what's going to happen there is that the client is actually looking at the past from a viewpoint in the future, because it's going to take time for his commands to reach the server. So keep that in mind. So when you play a game, you're looking at the past from a viewpoint in the future. Everyone is looking at a different past and a different further in the future at a different time. So it's kind of this kind of absurd time travel nonsense that network programmers we have to deal with to balance everything and have this illusion on screen that everyone is actually playing in the same world at the same time. Another concept, the snapshot buffer. So what is the snapshot buffer? So it's actually a buffer of snapshot on the server. On the server. So why we do that? So that the server is keeping a buffer of all the latest snapshot that is sent to the client. We do that to improve the hit detection. Because since everything takes some time to travel over the network, let's say you try to headshot a fast-moving enemy at frame 42, right? So you put your crosshair over his head, you shot at that frame 42, and that command packet is now in flight to reach the server. But by the time it reaches the server, that fast-moving player you were shooting has now moved somewhere else, and it's actually already somewhere else by the time you shoot, so the hit is not going to register. Even on LAN, the latency is enough for your hit to miss on fast-moving targets. So what the server is actually going to do is going to be able to go in his snapshot buffer and be able to take the snapshot 0 and 50, because those are the two you were interpolating between, and it's going to be able to interpolate at the same frame 42 using the same interpolation algorithm that the client was using to render his frame, and it's going to be able to process the hit detection at that frame. So this greatly improves the hit detection accuracy. So you're able to shoot at what you see on screen and really hit your target. So the tools that we use, the classic tools that we use as a network programmer, CPU profiling is probably the one we use the most. We use that to detect bottlenecks. We can see if a function takes too much time, where do we waste some milliseconds over a frame. So that's used a lot. Network profiling, of course, to see if there's bottlenecks over the network, to look at the ping and that kind of stuff. We also use a lot of shaping just to stress the netcode, see how it reacts with packet loss, that kind of things. We also look at bandwidth. You might be wondering why we look at bandwidth for latency. It isn't just like the size of the pipe. Bandwidth has an impact on latency because if you have some spikes of bandwidth, like you see on this graph, there are a few spikes. What's going to happen is all those packets are not going to be able to go through all at the same time, so they're going to get buffered on the router or whatever your connection is using, and because you're going to hit the cap. And because they're buffered and delayed, this is going to introduce some latency, and it might even fragment the packets, and it's going to take time to reassemble the packets. So yeah, bandwidth can introduce latency. So we look at that. Log traces, asserts, when we play tests, try to play tests with asserts to catch problems. This is typical. And video recording, QA often are going to record their playtest session and are going to be able to send back videos with inconsistencies that they found there. And also in Call of Duty, we have the theater mode, which is useful and it can help to find some desync problems that we can find with that. But yeah, all these tools, we can get in a situation like we were in this situation where all these tools were telling us that everything is fine, but the playtesters were complaining that there was latency. So the idea of using the camera. So the concept is very simple, actually. You just use a camera. You put two events that are going to happen separately, and you record them. So in the case of controller to screen, you just put your controller, you press a button, and you have the reaction on screen. And then you look at the video file, and you're going to see these two events, and you count all the frames, the video frames. You count all the video frames between the two events, and you can multiply by the length of the frame, and that gives you the latency. So if your camera is 100 frames per second, that gives you 10 milliseconds per frame. And so if you count 5 frames, that's going to be a 50 milliseconds latency, right? So this is something we've been doing for a while at Activision to test the controller to screen. We've been doing that since the COD 4. Yeah, and the idea was to use the same concept, but for multiplayer. So we will record 2 screens side by side, capture an event on one screen, and measure how much time it takes to happen on the other screen. And why we do that? Because you might be wondering, well, why don't we record the screens separately with HDMI recorder and then try to time code them in a way and put them back together? The problem is that they are in 2 different universes. They're not synchronized. To be able to synchronize them, we use some time synchronization protocol, right? But that's part of the netcode. That's the netcode that is responsible for synchronizing the time. So it would be like validating the netcode using the netcode. So the idea of using the camera is that it's a neutral observer. It's like a third-party observer, and it's as close as possible to the player's eye. So if there's a problem, even with our time synchronization, then we're going to be able to detect it with the camera. So to be able to do that, you need a good resolution, a good camera. So started searching for a camera that was up to the task. And the first one I tried a GoPro. It's just a camera that I have at home. I use it on the weekend to record mountain bike race, so I just brought it to the office, give it a shot, see if it could work. Turns out it works pretty well. It's a very fast camera. At that time, it was just released, so it was 120 frames per second at 1080p. Since then, there's a new firmware, so it can go even higher, but yeah, at that time it was still quite limited. But it was working. I was getting a result, but I was not satisfied with the quality of the image. Because it's two 1080p side by side, recording with only one 1080p camera, the resolution was quite lacking, and the low light introduced a lot of distortion, and the lens has some distortion. So I was looking for something better. And at that time, there wasn't much. It was the GoPro and the iPhone. That's pretty much what was on the market, in the consumer market, for high-speed HD camera. Nowadays, 2 years later, there's a lot more in the market. You can find almost 100 frames per second 1080p cameras. But yeah, the iPhone works fine too, but it was still lacking in terms of resolution, and I wanted something better. So I was speaking with the guys at the mocap studio. I have friends there, and they told me, hey, why don't you try our mocap camera? So I was like, yeah, why not, sure. So thanks, Xavier. He sent me his XIM XIQ. It's a really cool camera. It's a 1-inch sensor in this tiny cube. And it's actually industrial-grade camera. It's used in robotic assembly lines, medical imaging, automotive crash testing, and of course mocap. So it's a pretty legit camera, very precise. This is what it looks like at my desk. So it's a very tiny cube. There's no box. There's no it's not like a full camera with a box with SD card. It's really just a little cube with a sensor and an API. So you need to connect it to a PC to record, and you need to put a lens in front of it. So my desk looks like that, with the two screens side by side to record. So it's important to have two identical screens to record. Otherwise, you're going to measure the delay between the two screens. So it doesn't matter if your panel is fast or not, as long as they are the same. So yeah, so you see the camera there is connected with a USB 3, so it goes to a recording PC, and my frame rate was actually capped by the speed my PC was able to record the data, because this camera sends an insane amount of data. It's 5 gigabits per second, and I was never able to record that much data. That's like 85 times what the GoPro records. It's completely nuts. I was using my PC, recording PC was using 2 SSD in RAID. The USB 3 on board was too slow, so I was using a PCI Express USB 3 card to try to get the most bandwidth. And even with that, I was just a fifth of what the camera was sending. So I was able to get 200 frames per second. Resolution was 2048 by 800, so it's like a super wide resolution, which is good for two 1080p screen side by side. And I was recording with a codec that is lossless. So I was not inducing any compression artifact. It was lossless, grayscale codec that I was using. Grayscale, why? Because the camera is actually a grayscale camera. There's no color there, which is fine because we're interested in motion, not the actual how pretty the colors are on the screen. What else? Also, since it's from the mocap studio, these guys are super hardcore about like the precision and the time code. So the tools that they were using to capture, I was using their tools, and I was able to set all the settings of the camera, like exposure rate, the frame rate that I wanted to get. So all these technical settings of the camera, I was able to really fine-tune them, and I was certain of what I was getting. And that's important because when I was using the consumer camera, I was never sure of what I was getting, because even if the file that is recorded is like, let's say 60 frames per second, it's a true 60 frames per second, the file. But what the camera is actually doing, some camera might actually extend, the sensor might capture more light or less light to compensate for a low light situation. So you're never sure how much light the sensor captured. But with this tool, I was actually getting an XML file with the time code of each frame the camera was recording. So I was certain of what I was getting, which is the whole foundation of this technique, is to know how long a frame lasts so you can multiply by the frames you count. So speaking of counting frames, That's the boring part of this technique. You record a lot of video files, and then you need to count the frames one by one. For that, you can use any tools that you like that is good at stepping forward, backward. You want a very fast tool, otherwise you're going to go nuts. And so this is what it looks like. The video frame. So you see all the flashing bars. So what I do there is I print some timing information on each frame, like the frame number, the snapshot number, interpolation time, and all that kind of information. And I change the background color on every frame. So when I look at it frame by frame, I can really see what I was getting. So when I count the frame, I step frame by frame like that. So on this example, I'm going to look at the shooting latency. So the guy on the left is going to shoot. So I'm looking for the first frame where I see the muzzle flash, like this frame. So it's in the middle of the screen. I take all my measurements in the middle of the screen so that it's the same on both sides. And then I count the frame until I see the change on the other side. And you see there, the lighting changed a little bit on the face. So you know this frame being drawn right now is going to be the one I want. But I want to take my measurement in the center of the screen on both sides. So I'm going to wait for the next frame there. So you see the muzzle flash there. So I'm going to take this frame. So that's 9 video frames at 5 milliseconds per frame. So that gives us a base latency screen to screen of 45 milliseconds. Or in terms of game frame, that's 2.7 game frames. So you do that a bunch of times. You can take like 50, 60 takes is good. You want to look at the min number you get, the max, the average, the variance, if you want to see if the numbers are all over the place or if they're like around the same average. And yeah, my advice to you, if you do that, is to keep a lot of data of what you do. Keep SDK version, video, graphic settings, all the settings of your camera, SDK versions, so that if you ever in the future want to compare about if you have a new hypothesis, say, oh, what if this has an impact, you can look back at your old data and see if it was the case and compare your whole test. Otherwise, you're going to have to re-record, and that's super tedious to do. So this test that I show you was just the screen to screen. That was the base latency, right? So you can test a bunch of action like jumping, shooting, that kind of stuff. We didn't find any problem there. It was all within what we expected. So we developed a bunch of other tests to see if we could find latency. So in this talk, I'm going to go through a bunch of these tests there to show you how we did it. First one is damage feedback. So this one is the delay between the shooting and the feedback for the victim, the feedback that is being shot. And for the attacker is the feedback that you're actually hitting with the hit markers. So the test is very simple. Just shoot the guy in the foot and get the reaction on the other screen. Then you can count that frame by frame. So again, you see the screen is being drawn from top to bottom, and you want to take the measurement in the center. So we were expecting to be fast on that. I mean, the team at Treyarch, they told me, okay, we did a lot of optimization on the server. So the script processing on the server frame has been improved. So we should get a good number there. And this is what we measured. So Black Ops 3 was actually 25 milliseconds faster than the benchmark. The benchmark, in this case, it's like the best in the franchise. I tested other Call of Duty games, picked the best, and I was comparing against this one as the benchmark. So we were faster than the previous best. So that was good. That was confirming the optimization that the team has done in the engine, but it wasn't explaining the problems that we were getting. And same thing for the hit markers. They were 33 milliseconds faster. So the next test that I did, time to kill latency. So time to kill is the delay between firing and the actual dying. So for the attacker, it's when you see the other guy die, and for the victim is when you see the muzzle flash and then you die. So why is this important? It's because if you're an attacker and the time to kill is longer, it's going to feel like the other people are invincible or your bullets are too weak, so it's going to feel like something's wrong. On the other side, from the victim point of view, if the time to kill is shorter, it's going to feel like your attacker is too powerful. It's like his gun is sniping you in one shot. So it's going to feel very bad. So time to kill has a big impact on the perceived latency from the players. So if we look at the sequence diagram, this is in a perfect world without latency, where all the commands are immediate. So you see the shooting command reaches the server instantly, the snapshot will reach the other client instantly, and then the death event will reach both sides at the same time, and they both will perceive the exact same time to kill, right? So this is the perfect world that we all dream about. But in the real world, it looks like this. There's latency there. So it's going to take some time for the command shoot to reach the server and then to reach the other client. And what you see there is that the perceived latency for the victim is going to be shorter than for the attacker. And why is it that way? You might be asking, why don't we do client-side prediction for the death so that it's the same thing on both sides? The reason we don't do client-side prediction for the death is because if there's a misprediction, so let's say we blow up the guy on your screen and then, oh, we get a snapshot, say he's not dead, and you're like, ooh, you gotta bring it back together. So it's gonna look very weird, so we don't do that. So everything that doesn't have client-side prediction, you're always gonna feel your ping on top of the action. And that's the theory. So we wanted to validate that the theory of the sequence diagram was matching what we were seeing in the game. So for that, I wanted to test all different cases, symmetrical ping, asymmetrical ping, packet drop, packet errors, reordering. So all different cases with network emulation to see if I could really break the time to kill and how much it would take to break it. But for that, I knew I was going to have to record thousands and thousands of deaths, and it was not going to be practical. So what I did is I developed a procedural tool right away to be able to measure programmatically the time to kill. And I used the camera to validate that my tool was telling the truth. So my tool looked like that, just killing people over and over, and then it records the samples. And you actually don't need a camera to measure that because this is all happening from the one-time referential of one client. So it's all in one clock. So you could just record with an HDMI recorder and count the frames. So this is not something you absolutely need a camera for. And yeah, so I was able to record thousands and thousands of deaths like that. I watched this all day, guys. So the numbers I got, they were actually pretty in line with the theory. So you see the attacker always sees time to kill, that is the actual time to kill plus his ping plus a server frame. And that was matching what we expected, and we didn't find anything that was standing out from that. Another thing to keep in mind for time to kill is you don't just want to look at the average, because it's going to average out the edge cases. So you want to bucket your measurement into buckets and see how often you see an irregular time to kill. But yeah, I was able to break it, but it was way outside of the TCR range. It was with crazy network emulation. So it was not the problem we were seeing in the playtest. So the other test, line of sight latency. So this one is the you see me, I see you latency, the delay between when I spot you and you spot me. And why is this important? This one is very important because Call of Duty is all about surprising your opponent. Like you run and gun, and the first one to start shooting is going to tell the server first that he shot. So it's very important that the I see you see me latency is very as low as possible. So to test this one, I did this test where I'm just strafing left and right, getting in and out of line of sight with the occlusion of a wall. So it looks like that from the camera. And in slow motion, that's what it looks like. So for this one, you need to pick a reference. So what are you going to use as the ICU reference? Are you going to use the first pixel that is sticking out, or so what are you going to use? So I use the head because Call of Duty is all about headshotting. There's a huge damage modifier for the head, and the players are actually aiming for the head. They know exactly on each wall where they need to put their crosshairs, so when the guy appears, they're going to shoot the head. And also, if I look at the elbow or the foot, it's going to give me some very inconsistent result depending on the walk cycle and the animation. So I was really using the head for that. And it's in the middle of the screen also on each side. That's very important. So for this test, we were also expecting to get a good result because the team has done a lot of optimizations. We had doubled the snapshot rate. We had doubled the client rate. We had reduced the interpolation as low as possible, and a bunch of optimization here and there in the netcode. So the team was expecting to get a good result there. But this is what we got. We were 60 milliseconds slower than the benchmark. So that was a surprise, because we were expecting to be faster, and we were much slower. So at that point, we knew, okay, we find something wrong. We hit something that's very wrong, and we need to fix it. So we thought it was going to be easy from there, but it turns out it wasn't so easy. So I'm going to show you how we found that problem. So searching for the culprit, I went through all the netcode. I was looking at maybe it's snapshot interpolation, maybe it's client-side prediction. Is it a bug in the netcode? Is it a performance issue? And I wasn't finding anything. I almost audited the whole netcode, and everywhere I was looking at, I was kind of finding that, well, this should be faster, this should be faster. So that was very confusing as to why the camera was picking up such an additional latency. So at one point I was like, okay, I'm not finding anything from top down, so I'm going to go write a procedural test. Try to do something programmatically, try to replicate the test of the camera, but with code. So what I did is just a little test like that, where the player is strafing left and right, crossing a line. And every time he was crossing the line, I would dump a huge amount of data. Everything I could get my hands on, a timer, a frame timer, a snapshot timer, network time, anything that could be potentially relevant to the latency, I would dump it at the moment the player was crossing the line. And I replicated this test in all the previous Call of Duties that I was measuring against. And what I found was this. At 10 Hertz, the snapshot rate, we were faster by 30 milliseconds than the benchmark. At 20 Hertz, we were 40 milliseconds faster. And at the target rate that we wanted to ship, because we wanted to ship at double the snapshot rate, so we would have been 90 milliseconds faster by just looking at my procedural test. So something was very wrong there. My test that I thought was replicating what the camera was seeing was not giving me the same numbers. There was a big discrepancy there. So at that point, I was kind of confused, but also I was happy to see, well, the netcode seems to perform much faster. So that's good news, but where is the latency coming from? So at that point, we were like, well, maybe it comes from the graphics, maybe it comes from the animation. It has to be somewhere after the netcode, because the netcode seems to be faster. So first thing I tried disabling the animation. So I put the player in T-stance, strafing left, right, like that, and redid my camera test. And what I found was this. The exact same thing, the exact same gap. So we were 30 milliseconds faster. So that was the first time that the camera was telling the same story as my procedural tool. So they were lined up. So I was like, okay, I have an animation problem. So that was good. But where in the animation? What was the problem? So I did some profiling to see if there was a bug or a performance issue with the animation system. Turns out it was working. It was working as intended. So it was not a performance issue. So I was kind of scratching my head, and see, I was looking at the data. Maybe there's something from, I don't know, from the data that can induce a latency. And see, this is Ghost. And if you look the animation style, I put the white marker over the head. That's the position of the entity. That's what we put in the snapshot that we send over the network. That's what my procedural tool was using when I was crossing the line. But you see, the head is always slightly ahead of the marker. So the player is leaning in the direction of the movement, and the other side is leaning. So it's a symmetrical animation on both sides. But it doesn't seem like it's much, because the player is always centered on the entity position. But looking at Black Ops, look at the animation style. It's different. It's not a symmetrical animation. You see, he's walking backwards when he's strafing left. So that means the head is actually ahead of the entity marker in one direction, and it's behind in the other direction. But yeah, I wasn't expecting this to be a big problem, but I thought, okay, let's look at strafing left and right separately using the camera to see if that makes a difference. And this is what I found. 100 millisecond difference between strafing left and strafing right. So that was a big surprise because all my tests before, when I was doing my tests, I didn't consider left or right separately. I was putting all the numbers together in Excel, and they were all like averaged together. So yeah, so that was a big surprise. So I thought, okay, let's do another test. Just measure really the delay between the marker and the head that I see on screen. And this is what I found again: 87 milliseconds or 90 milliseconds slower going left than right. And you see there, there's negative latency. That means that we can beat the network latency by actually putting the actual model a little bit ahead of what we synchronize over the network, because we're going to see it ahead of time, and that's more than the network latency. So we thought, that's interesting. We can hide some latency with just tiny offsets that are not so visible on the screen. So we thought, why not use this on purpose all the time? So we thought, okay, let's try to just offset our strafing animation left and right a little bit on each side based on the velocity of the speed of the player. So we tried that. We actually developed a tool for the animators to be able to recalibrate all their animation. So you see the tool, what it's doing there is I just draw a sphere where I want the head to be. And the sphere is going to turn green when the head bone is within a tolerance of where I want the head to be. So in this example, I'm hiding about 35 milliseconds of latency. Why 35? It's because at some point you reach a limit where if you try to hide too much, if you're too greedy by how much you want to try to hide, it starts to look weird. The style of the animation is going to look off. So we kind of went as far as we could by still keeping the aesthetic of the animation. So you see, that's one frame when going right. Going right was pretty much okay. You see the pink line. It's the center. It's the center of the entity, the position that we put in the network packets, and we put the head slightly ahead. And going left is the one we had to change a lot. And you see of course, the ass is going to stick out the same way the elbow is going to stick out on the other way, but that's kind of part of the models of the game. It's part of the gameplay. Like if you have a long sniper rifle, your muzzle is going to stick out of the corners and that kind of. So you need to be aware that the size of your character has an impact on the visibility. But what's important is the headshot. So we thought it was completely unacceptable to get 90 milliseconds advantage when strafing left when you could headshot someone. So once that was fixed, we redid the test. And this is what we found. We were now 100 milliseconds faster and 42 milliseconds faster than the benchmark. And see, this is how it was before, just to show you the gap that it was before. And I really want to pause there so that you can let that sink in. I'm a network programmer. I write netcode all day. I try to optimize my stuff, try to make everything go as fast as possible in the netcode. I try all the tricks. I try to pack more bits into a byte if I can. It doesn't work, and so the idea is that if I was ever able to reduce the ping of everyone by, let's say, 30 milliseconds, that would be a huge accomplishment for me in the netcode, and I will open a bottle of champagne or use the emoji at least. I don't know. But this was worth 90 to 100 milliseconds of latency. So that was a big surprise for me. I was not expecting this at all, that the data would have such a big impact on the perceived latency. Because it's not true latency, it's really the perception from the player. You're going to get an advantage when you strafe to the left. You're going to get 90 milliseconds advantage to headshot the other guy before he's even able to headshot you because he's not seeing your head yet. So once we had that, we wanted to test all the animation in the game because that was one animation. So this is all the animations in the game. Thank God for QA for that. They were able to test them all. So I modified my procedural tool to consider the bone of the head instead of the snapshot position. So with that tool, they were able to test all the combinations, and they found a lot of problems actually, and we were able to fix most of them. I won't say we fixed them all because at some point, some of them were just a little bit outside of the range that we wanted to get, but the animators were telling us, okay, that's as much as you're going to get because it's going to look too weird if we go too far. So at some point, you need to compromise to get the aesthetic right, but that was able to at least get everything pretty much lined up. So just to do a recap of the workflow so far of how I use the camera. So the first step is I use the camera to measure a problem on the screen. Once I found a problem, I try to isolate it with a procedural tool, and I want to make sure that my tool is telling the same story as my camera. Once I have that, now I can iterate very fast using my procedural tool, so I don't need to use my camera anymore. So I can fix the problem, trying different things, and I can iterate very fast. And after that, I can prevent regressions from re-happening by using that procedural tool. So the idea is not to use the camera every day and count frames every day, every time you make a change in a line of code. It's really to get the perspective from the eyes of the player once, develop some new tools, confirm that your tools are working as you think they are, and then use those new tools that you have a bigger confidence in. And I would add a fifth step there that we didn't get to, is to automate that in your constant integration system. So every time you submit a change list, you're able to catch regressions faster. So I've shown you the three first tests. So let's look at the next two. So stance change, it's very similar. Stance change is when you go from standing to crouch, crouch to prone, and those kind of transition. Again, if you can see the other players faster than he's going to see you, there's going to be a competitive advantage there. So the test looks like that. Which one do you think is faster, going down or going up? It's hard to tell. See, going down has a lot more latency. This is because we want the responsiveness of the client-side prediction. When we press crouch, we want the animation to start right away. But when you're going up, we have the animation start right away, but because it takes some time to go up, we can actually cheat by slowing down the first-person animation and let the third person go faster and catch up. So it's going to be able to catch up with the first person, and they're going to come up at the same time. So with that, we were able to validate that it was faster than the benchmark. We actually found that the prone to standing was a lot slower, so we were able to fix that one by slowing down the first-person animation. The next test, hit detection fidelity. So this one is very important because if the hit detection doesn't feel right, if you miss your hit, it's going to feel like there's a lot of latency in the game. One thing we knew that was like a difficulty or problem, a limitation in the game since the very beginning is that the snapshot buffer was not containing the animation state. It was only the positions of the players. So when the server was processing the hit detection, it was putting everybody back to how they were at a specific frame, but the animation state was the present animation state. So that means if a player changed states, the hits, there was a possibility that the hits will miss. And players were able to find that out, and they use a technique called the drop shotting, which means that when you see an enemy, instead of starting to shoot, you just drop to prone right away, and after that you shoot. So the other guy is going to try to shoot you where he sees you, but his hit are going to miss, because as you see in the diagram, the shooting and the prone arrive at the same time, but it's going to take some time for the prone to reach the other client. So there's a gap there of missed hits because the server is not considering the animation state for the hit detection. So this is something Treyarch wanted to fix. They wanted to invest the resource. It's very expensive to fix this kind of bug because you need to store more data, you need to process a lot more data on each bullet that are fired. But they wanted to fix that because they felt that it's a legitimate technique. I mean, if you drop, if you change your stance, you're going to be harder to shoot at. But they wanted this technique to be tunable by game designers so that it's not it's relative to the speed of the animation, not the ping of your victim, right? So I was able to validate that this change was working. You see there, that's the previous code. I changed the game to shoot a bullet on the exact same frame that the guy goes to crouch. So he's shooting, he should hit, but the hit is missing because there's no rewind of the animation state there. And here, after we implemented changed the animation state, this is with 200 milliseconds of latency. So you see there, we're able to process the hit correctly, so you can really shoot at what you see on your screen. So we did a bunch of tests with symmetrical, asymmetrical ping to see how it was working, triple packet drop, a bunch of network emulation settings. We were able to confirm that it was working 100% of the time with all our settings that we were testing. But again, even with that, the team was still nervous to release a change like that because it's Call of Duty. Players are very used to the feeling of the game, and they were nervous that maybe players don't like that. So what we did is a blind A/B test. And in this case, the bigger bar is better. We asked the testers to give us a feedback of how they felt the latency. 10 was flawless, and 5 was average, and 0 was terrible. And we were very surprised by the result. Testers didn't know which build they were testing. And yeah, the new netcode was pretty much well received compared to the original one. So with that, we had the classic tests with the procedural tool. We had the camera confirming that it was good, and also had an A/B test that was also confirming. So with these three different tests, Treyarch felt very confident that they were releasing something that was an improvement. So next, the controller to screen latency. So let's talk a little bit about that. This is what we measure by when we record a button press on the camera and measure the reaction on the screen. And we actually don't use like putting your finger like on the gamepad because it's very hard with the camera to find the exact frame where your thumb press the button. So what we use is an instrumented gamepad like that. Ben Heck is the guy who does these custom gamepads. So what happens is when you press a button, there's a LED that's going to turn on the panel. So it's going to give much better contrast with the camera. We're going to see the exact frame where the LED turned on to be able to take precise measurements. So this is what it looks like in slow motion. I'm going to press A to jump. You see the LED is turning on, and we can measure the delay there. But when you do controller to screen, it's always good to know how much your panel is worth in terms of latency. So for that, I used the video signal input lag tester from Bodnar. Just a simple device. You connect to your panel, and you can measure the latency. It's going to give you measurement at 3 positions on your screen. So this one, this was a 1 millisecond advertised panel. So I was getting about 10 milliseconds in the middle of the screen, which is pretty good. And it's also good to use to compare your two panels. So even if you bought the same model of your monitors, you can confirm with this device that really they are having the same latency. Another thing that's good to know is your dev kit's minimum latency. You want to know how much is coming from the gamepad and the dev kit. So the trick there is to just write a simple program that's going to just pull the input as fast as possible and render that on screen as fast as possible. And with the camera, you can measure the controller to screen latency the same way you did with your game. But you know that there is just the bare minimum. It's just down to the absolute minimum that your dev kit can do. And I'm not going to give you the numbers there for each platform, but now you know how to measure it, so you can go ahead and test your dev kit. Controller to screen latency. So this was on this was the test on console. This just to give you the evolution throughout the development of the game. When we started, we had a big problem. There was a lot of controller to screen latency, and we didn't know where it was coming from. I'm not going to dive into how we solve all the problems because that could be a talk in itself. So I'm just going to like show you like I did how to measure it. And yeah, the good thing about that is that, I mean, why it's important, it's because as a network programmer, the controller to screen latency is going to have a big impact on how it feels in the playtest. So you want to make sure that it's as low as possible, and you want to kind of take ownership. I mean, you're not going to be the graphics guy, you're going to make all the big changes, but you want to at least be there to help them and guide them to help measure their stuff. So with my camera, my mocap camera, I was able to help them get some measurement and validate some assumptions that they were having with their changes. It's funny because sometimes they're going to tell you, oh, I made some change list. You're going to see it's cutting 1 frame for sure, and you measure it and there's no difference. So it's good to be able to validate that. And yeah, we were able to match, to finally match the benchmark in the end. So as a summary, screen-to-screen latency, we're able to get 68% less than the pre-alpha, and we ship with 45% less than the benchmark. Controller to screen, 35% less than pre-alpha, parity with the benchmark on console, and PC, they were able to go further with 22% less than the benchmark on PC. The hit detection, we're able to improve the fidelity using the animation state, and yeah, that was the score from the playtest, and this is a quote from the QA. It's always good. So future development, what can we do next? So a lot more testing coverage, for sure. I'll show you a bunch of tests that I did, but there's a lot more tests that can be done. For example, we don't check audio latency. They can have a big impact on the perceived latency of the players. More automation to make sure we catch regression faster. There could be improvements to the recording equipment. Better camera could help to get more precision. Also, using broadcast tool, like dual channel HDMI recorder that are very precise, that they record both channels on the exact same frame, that could be used also. So there's a lot of things that can be looked into. Photo sensors, something we played a lot with actually. It's very promising. Photo sensors are very fast, and they're going to pick up the change of color or of light on your screen, and something you can automate as well. So there's a lot of stuff that can be done with that. And in terms of tech, to improve the latency in Call of Duty, snapshot rate is one of the big things. If we could increase the snapshot rate, that will reduce the latency. But it's not all about snapshot rate, because that's kind of the brute force approach. There's also using events, being able to sync some parts of the snapshot that is important to get a lower perception of latency. Because it's all about perception. It's not just the actual time it takes for the packets to reach one side to the other. It's really about how the player perceives it. And sometimes it can be something like the animation is slow to start, or the kind of things that I've shown you. So that's pretty much it for my presentation. I hope the biggest takeaway is that it made you curious to test your game with a camera. And you don't really need a mocap camera for that. You can use your iPhone. And yeah, just get a ballpark idea, and it's going to tell you if your tools are really measuring, or if your tools are really telling you the truth. All right, thank you.